Let's talk about our map of reality. You know, the light hitting your screen, the very stuff you're made of. It's all described by this incredible theory. But here's the thing. It wasn't just dreamed up by some genius in a lab. This is the standard model of particle physics, and the key word here is discovered. It was found piece by piece, and it all started with something super simple, a weird glow in a glass jar. So this is it, our map of reality. And yeah, I get it. At first glance, it looks intense, right? You've got all these names, quarks, leptons, gauge bosons, and of course, the Higgs boson. It looks like this perfect, finished product. But remember what I said, this map wasn't invented. It was discovered, one piece at a time, by scientists who were just trying to make sense of a world they were observing. And that's the real story here. I mean, where did this thing even come from? How in the world do we piece together the fundamental rulebook for, well, for everything? Was it just some grand theory cooked up on a blackboard? Or was it something more grounded? Was it built clue by clue, just by carefully watching the world around us? Well, the answer is way more down to earth than you might think. This didn't come out of a supercomputer or some divine inspiration. Nope. The entire journey, this whole incredible map, it all kicked off with a really simple observation, a weird spark inside an empty glass jar. So that's where we start. Not looking up at the stars, but inside 19th century labs. You had these scientists who are basically just messing around. They wanted to see what would happen if they shot a bunch of electricity through a vacuum. And what they saw was this bizarre beam of light, this glow that just zipped from one metal plate, the cathode, to another one, the anode. They were definitely observing something, but they had no idea what it was. And that simple act of just watching a strange light, that was the very first step into the subatomic world. So they started studying these glows like crazy. And pretty soon, the first pieces of the puzzle fell into place. Back in 1897, J.J. Thomson noticed that these cathode rays would bend toward a positive charge. That meant they had to be made of tiny negative particles. We call them electrons. Then just a year later, by looking at rays going the other way, they found a much heavier positive particle, the proton. All of a sudden, the unbreakable atom had parts, and it was all figured out just by watching sparks in a jar. How cool is that? Okay, so finding the electron and proton, that just opened the floodgates. From here on out, it wasn't just random experimenting. It turned into a full-blown cosmic detective story. Every single time physicists saw something weird, something that just didn't add up, they had a hunch. There must be a new, undiscovered particle out there that's causing it. And check this out. What's so cool here is that every one of these discoveries was a direct answer to a problem they could see. Light was acting weird, so Einstein goes, maybe it's made of particles. And boom, the photon. Atomic cores were way too heavy for just protons, so Rutherford says there must be a neutral particle in there. Hello, neutron. Energy just seemed to disappear during radioactive decay, so Pauli suggests the neutrino. See the pattern? Each new particle was basically a suspect brought in to solve a specific crime. Let's just zero in on the neutrino for a second, because this is the perfect example of what I'm talking about. Scientists are watching neutrons decay, and the numbers didn't add up. The energy coming out was less than the energy that went in. I mean, that's impossible. It violates the fundamental laws of physics. So Wolfgang Pauli proposes this ghost particle that must be sneaking away with the missing energy. He literally made it up just to balance the checkbook. And get this, it took another 26 years before they could actually find one and prove he was right. So this whole method, seeing a problem, proposing a particle, it worked. It worked really well. A little too well, actually, because it created a whole new problem. By the middle of the 20th century, physicists were finding so many new fundamental particles that the simple, elegant picture they were hoping for, well, it was turning into a total mess. You see, as our particle accelerators got bigger and more powerful, we just kept smashing things together harder and harder. And every time we did, we found more and more new particles. The list just kept on growing. It was absolute chaos. They literally called it the particle zoo. That beautiful, simple picture they were searching for? Gone. Replaced by this huge, confusing jumble of particles that didn't feel fundamental at all. And then, another breakthrough. And guess what? It came from trying to explain the observations. A physicist named Murray Gell-Mann looked at this whole zoo, at all this chaos, and he saw patterns. He had this brilliant idea. What if most of these particles aren't fundamental? What if they're actually made of even smaller things? And he called these smaller things quarks. And this is just a perfect way to show how it worked. Take the proton. We've known for ages its charge is exactly +1. How do you get that? Well, with the quark model, it's like a simple recipe. You take 2 up quarks, they each have this weird +2/3 charge, and you add 1 down quark, which has a -1/3 charge. Do the math, and what do you get? Exactly +1. Just like that, the quark model started bringing a beautiful order back to the chaos.
So here's the key takeaway. This new model gave us a much deeper way to understand things we were already seeing. Remember that neutron decay we talked about? Before quarks, it was just magic. One particle just poofs into another. But now with the quark model, we could see what was actually going on under the hood. A down quark inside the neutron was literally flipping into an up quark. It was a much more fundamental, and honestly, a way more satisfying explanation.
Okay, so now with quarks in the picture, physicists could finally start sorting everything out. They could organize all the particles they'd ever seen into a structure that actually made sense. So let's look at the final pieces of the puzzle and see how we get to that complete map. So with this new framework, it turns out all the matter we've ever seen can be sorted into 2 neat little families. First, you've got the quarks. Think of them as the social butterflies. They love to clump together to make bigger things like protons and neutrons. Then you have the leptons. They're kind of the opposite. They're the light, antisocial particles like the electron and that ghost, the neutrino. And that's it. That's the fundamental stuff that makes up our universe. But, just having stuff isn't enough, right? Something has to hold it all together. Something has to make it all interact. That's where the forces come in. And in the standard model, forces aren't some spooky, invisible thing. Nope, they are also carried by their own special particles, which we call gauge bosons. And here are the big ones. You've got the strong force, carried by gluons, which, you guessed it, glues quarks together inside protons. Then there's the weak force, carried by W and Z bosons. That's the one that lets quarks change flavor, which is what's behind radioactive decay. And finally, electromagnetism, carried by the photon. That's light, electricity. It's literally what's letting you watch this right now. And again, every single one of these was added to the model to explain something fundamental we observed about how the universe behaves.
We are so close. There was just one last, giant mystery. Why does anything have mass? Why do particles weigh anything at all? The final piece of this observational puzzle was the Higgs boson. It's the particle that comes from this universe-wide energy field that basically drags on other particles as they move through it. And that drag is what we feel as mass. So let's go back to that map we started with. When you look at it now, it's not just some intimidating, abstract chart anymore, is it? Every single particle on here, it represents a mystery that got solved, a puzzle that was pieced together from clues, an observation that demanded an explanation. This thing is a testament to more than 100 years of incredible scientific detective work.
So there you have it, the fundamental structure of reality as we've observed it. You've got 6 quarks and 6 leptons that make up all the matter. You've got 4 kinds of bosons that carry the forces, plus the Higgs to give everything mass. But observation also showed us something really, really weird. All these particles seem to come in 3 distinct generations, 3 families, and each generation is heavier and way more unstable than the one before it. And that leaves us with one last massive question. This entire model built from the ground up by observing the world tells us there are 3 complete sets of these matter particles. But everything we see and touch, you, me, this planet, the stars, it's all made almost exclusively from that first, lightest generation. The other 2, yeah, they exist. We've made them in labs, but they pop into existence and then vanish in a fraction of a second. So why are they even there? Why 3 generations? That's a question the standard model points to, but it doesn't have an answer for. And it's the perfect reminder that this incredible story of observation is nowhere near finished.